Problem 3. Calculate the drift velocity of electrons in germanium at room temperature and when the magnitude of the electric field is 1000 volts per meter. Under these circumstances, how long does it take an electron to traverse a 25 millimeter length of crystal? So the drift velocity can be calculated by this equation. This drift velocity is equal to mu E times E, where E is the electric field intensity, okay, in terms of volt per meter, and mu E is the electron mobility. The value of the electron mobility over here for the germanium electron is given in table table 18.2 of the book. So the value is given as mu E in this case is given as 0.39 meter square per volt second. So just apply these values. So the drift velocity will be equal to 0.39 multiplied by E, which is 1000. So it will be 390 meters per second. The answer given is 380 meters per second. This is according to 0.38 meters square per volt second. So in some books, the value of the drift velocity is the value of this electron mobility is 0.38. So it depends on what is the value of this. So this is part A. Part B is the time it takes. So we know that the time is equal to the distance divided by velocity. In this case, distance is 25 millimeter, which means in meters this is the distance. So divided by 390 meters per second. So this will be the time. So it is 6.41 into 10 to the power minus 5 seconds. Problem 4. At room temperature, the electrical conductivity and the electron mobility for copper are 6 into 10 to the power 7 ohm meter inverse and 0.003 square meter per volt second respectively. Compute the number of free electrons per cubic meter for copper at room temperature. What is the total number? What is the number of free electrons per copper atom? Assume a density of 8.9 gram per cubic centimeter for copper. Okay, so we can use this expression for finding the number of free electrons, where n is the number of free electron, E is the charge on the electron, mu E is the mobility of copper electrons, and sigma is the conductivity. Okay, so just input these values. 6 into 10 to the power 7 ohm meter square, and we need to find, and the charge in one electron is 1.602 because this is a constant. 1.602 into 10 to the power minus 19 coulombs. This is the charge on one electron, and mobility is 0.003. So from here I determine, so n is equal to 1.248 into 10 to the power 29 atoms per cubic meter. Okay, so in 1 cubic. So in this case, now we have found that this many atoms per cubic meter. In the second part, what we have to find is what is the number of free electrons per copper atom. So we have atoms in 1 cubic meter. So sorry, we have number of electrons. It's not atoms. Okay, number of electrons per cubic meter. So what we need to find is how many atoms are there in 1 cubic meter. Okay, so for this we can find this number of atoms in 1 cubic meter we can find from this equation, which we have already used in some previous chapter. So which is the number of copper atoms. This is N is Avogadro number 6.022 into 10 to the power 23, and rho is the density 8.9 gram per cubic centimeter. Okay, so 8.9 gram per cubic centimeter, and the ACU is the atomic weight of copper, 63.55. Atomic weight of copper is 63.55 gram per mole. Okay, so in this way we will find the number of atoms in per cubic centimeter. Okay, so if I will calculate it, then this value will be equal to, so we get 8.43, okay, 8.43 into 10 to the power 22 atoms per cubic centimeter. Okay, we need to convert it into per cubic meter. So we know that 1 centimeter is equal to 10 to the power minus 2 meter. So minus 2 times 3, 10, then it will be minus 6, and then it goes up, then it will be plus 6, so it will be 8.43 into 10 to the power 28 atoms per cubic meter. Okay, so now we have this much number of atoms and this much number of electrons. So how many electrons per atom? That means the ratio of this, it is equal to 8.43 into, oh sorry, it's it will be equal to 1.248 into 10 to the power 29 divided by 8.43 into 10 to the power 28. Okay, so I will calculate it. So I calculate it to be 1.48. So this means that there are 1.48 electrons for each atoms. Well, these are not just the total number of electrons, these are the free electrons. Okay, free electrons. Problem 5. A cylindrical metal wire 2 mm in diameter is required to carry a current of 10 ampere with a minimum of 0.03 volt drop per foot, or 300 millimeter of wire. Which of the metals and alloys listed in this table are possible candidates? Okay, so in this case what we can do, because in this table you can see that electrical conductivities are given, so the wires which we should choose must have the electrical conductivity higher than needed. So what electrical conductivity is needed? So this we can find using these equations. Okay, so first of all we will find the resistance. Okay, or the resistance we can find by this equation. So voltage difference is 0.03 volt per foot. Okay, so voltage difference is 0.03 volt, and the current is 10 ampere, and the resistance will be this. So from here we can find the resistance, which is equal to 0.03 divided by 10. Okay, so the resistance is 0.003 ohm. So next we can find the resistivity. Resistivity is 0.003 ohm multiplied by the cross-sectional area, pi, divided by 4. Diameter is 2 millimeters, so it is 0.002, and then the length. Okay, in diameter is required to carry a current of 10 ampere with a minimum of 0.03 volt drop per foot. So the length is per foot, or we can take it in millimeter as equal to 300 millimeters. So 300 millimeter is 0.3 meter length. So this will give us the resistivity value. So the resistivity value is 3.14 into 10 to the power minus 8 ohm meter, and the conductivity will be, conductivity is sigma, will be equal to 1 over rho. So 1 over 3.14 into 10 to the power minus 8. So this will be equal to, so this is equal to 3.18 into 10 to the power 7 ohm meter inverse. So we need to find the values of we need to find the metals which have electrical conductivity greater than this value, 3.18 into 10 to the power 7. So all values over here are given in terms of 10 to the power 7. So we can see that silver is 6.8 greater than 3.18. So silver is acceptable, copper is acceptable, gold is acceptable, aluminium is acceptable, brass is not acceptable, iron is not, platinum is not, because these have conductivity values less than the needed values. So we will choose aluminium, copper, gold and silver. We can choose.